In this lecture, I will continue our discussion on cache memory and different mapping techniques. So far we talked about direct mapping and fully associative mapping. Okay, in let me check my microphone. Okay, it's recording. In fully associative, I said that each address field, which will divide it to two parts. One part is tag and the other part is offset. The offset determines the location of a byte inside the block, and the tag in fact like is identical for each block of the main memory, which will be mapped in the cache memory. So when we access the cache memory, all tags are searched in parallel to retrieve the data quickly. I'm saying that the tag are searched in parallel. So this one is the disadvantages of as a fully associative technique to direct mapping, because in direct mapping any block that we were looking for in the cache, we calculated the block number of the main memory modulate the number of blocks in the cache, and then we only check the tag of that specific cache block. But here we need to search all the tags in parallel. Okay, we already discussed the fully associative mapping in the previous lecture. So today I'm going to talk about the other technique, which is a combination of direct mapping and fully associative mapping, and it is called n-way set associative. So this one, in this mapping, the cache mapping is like direct map cache in that like a memory reference map to a particular location in a cache, but unlike direct mapped cache, a memory reference map to a set of several cache blocks, similar to the fully associative. Instead of mapping anywhere in the entire cache like a fully associative, a memory reference can map only at a subset of cache slots. So let me show you the structure of fully associative cache, so it will be easier to understand if I show you the like a cache structure for fully associative for sorry n-way set associative. If we assume we have a cache like this and it has, let's say, 8 blocks. Okay, 8 blocks. So block 0, block 1, block 2, block 3, block 4, block 5, block 6, and block 7. Okay, so of course we can do direct mapping, we know how does it work. We can do associative mapping, we know how does it work. But what is n-way set associative? First of all, each block has its own tag. Okay, all of them are tags. And for example, in this specific example, we assign each two blocks to set. So we call block 0 and block 1 as set 0. Block 2 and block 3, we assign them to set 1. We block 4 and block 5, it's set 2, and block 6 and block 7, it's set 3. Now here, when we have a main memory, let's just show a main memory. When we have a main memory, okay, and like a specific location of a memory, if first of all we look to this mapping as direct mapping for the first first step, so we calculate the modulate of the block number to the number of sets, not number of blocks. Okay, so if it is let's say block number 15 in the cache, okay, 15 in the cache, so we say uh, let's say 17 should be better, block 17. So we say block 17 modulate 3 is 2. Is it correct? 3 times 5 is 15 and plus 2. So block 17 will be mapped to set number 2. Set number 2. So block 17 goes to set number 2. Here so far is like direct mapping. But here is a difference. Inside set of 2, block 17 of the main memory can be copied of any of these 2 blocks inside set 2, any of those which is empty, which is available. Okay, so if b4 is available, b17 will be copied to b4. If b4 is taken, like it will be copied in b5. So in order to determine the number of set, the processor works like direct mapping, and inside each set we consider it as fully associative mapping. So it's a combination. Okay, so it has the advantage of both fully associative and um, direct mapping. Okay, so this one is the way that the processor work, sorry, the n-way set associative work. And now let's look to the address field. Okay, first of all, which fields should we have? Of course we should have tag. Okay, we all know that we have tag. We will have offset. Why we need offset? Because offset determines the location of byte inside the block. And what else do we need here? Here, because we don't need to like have a field block, because these blocks are like working like as fully associative. The thing that we need to have as a separate address field is the number of set. So we say set. Okay, so this one is the address field for n-way set associative. Okay, so n-way set associative map. Tag set offset. Okay, so when we have this address, the first thing the processor does finds the set number of the cache which the block will be mapped or will be copied by dividing the number and calculating the remainder. When the set is determined, checks the blocks inside each set. Any of those are available, we can replace it like with that block. But before continuing to the next part, the question, when we come to set 2 in this example, and both both of them are full. Which one we should like kind of over overwritten? Which one should we like? We should write the block 17, overwrite the block 17 on which data? There are some like some there are some different ways, okay, to determine which block should be erected and the data overwritten on those block. The same thing for fully associative. In fully associative, I said that when we have a map, we have a cache, a block can be written in any of these blocks. But if all of them are empty, all of them are full, which one we should choose to overwrite the data on like that specific block? So we have three different techniques. First one is FIFO. The next one is, we might have LIFO as well. We have least recently used, and we have last recently used. These are the ways that we determine which plug should be replaced in the cache if the cache is full. What is the FIFO? FIFO stands for first in, first out. So the first block in the cache which was like filled should be replaced. So if, let's make it simpler, let's say we have 4 blocks in the cache memory. At T5 this block is filled, T7 this block is filled, T2 this block, and T8 this block. And it's time. T means time. So we want to write a new block here. We should write this block, overwrite this block on which of these blocks. We look which one is mapped, or which one is entered to the cache first. Of course, T2. Okay, so this block has been filled first. So we replace it with T2. The next technique is LIFO, last in, first out. It's the opposite of FIFO. So T8 is the last block that is entered. If we want to replace a new block with the filled uh, cache, we replace it with T8. Least recently used, it's not about time of filling. The time of the block was accessed. Okay, so let's say at T5 we access the block. If we just we put it T5, T8, T2, and T7, something like this. And then again we access to this block at T10, we access to this block at T12, we access to this block at T9, and we access to this block at T13. Now, so we copied them in these times, T5, T8, T2, and T7, but then again we access to those data in these times. Least recently used says which one of them has been used the minimum number, so the least recently used. So if we look to here, T13, T10, T12, T9, we see that T9 in fact is least recently used block. It was used at T9, and after that the other blocks were given access, but T9 is not. So although T2 was copied before T5, but because T2 was accessed as T10 and this one accessed in T9, so this block will be considered as least recently used. And most recently used is um, opposite of least recently used. Of course, most recently used is this block, and this block will be used to hold the new data. Okay, so this one is the techniques that we use. So again, so this one is the first copy at this time, and let's say here is last access. So FIFO replace this block. LIFO replaced this block. List recently used replace this block. Last recently used, list recently used, and last recently used replace this block. So we see that all of these four techniques replace a different cache memory. So which one is better? We don't know. We need to like decide. The designer decides which one is better. And so, but my favorite is uh, my favorite technique is list recently used. Okay, so if I design a processor, I will use definitely list recently used. Okay, so let's continue with NV set associative, and let's have one example. It says that we have a two-way set associative, byte addressable. We have a memory which is two-way set associative and byte addressable. Main memory is 2 to the power of 14, and cache has 16 blocks, and each block has 8 bytes. We want to find the address fields in this example. The first thing we see that the cache has, what we are going to find is we are going to find tag, set, and offset. Cache is 16 byte, and each set has 2 blocks, okay, because it's two-way set. So number of sets is equal to 16 over 2, which is 8. So we have 2 to the power of 3 sets. So set is 3. What is the size of each cache? Each block. Each block is 8 bytes. How many bits for 8 bytes? 3. What's the total address field? The total address field is 14. So what is the tag? It's 14 minus 3 minus 3, which is 8. So this one is the way we find the address field. So when we use this field, the first thing we calculate the address modulo the number of sets, and then compare the tag, and if tag is correct, we get the entire block and access to the offset. Another example, let's say we have a main memory of 1 megabyte, cache has 32 blocks, each block has 16 bytes, Okay, and now we want to find the like the location of the cache in which the address the address 326A0 will be mapped. Okay, so the question is at which location of the memory this address will be mapped. If we have direct mapping, if we have fully associative mapping, if we have four-way set associative. So for all these three methods, we want to access to this address of the main memory, and these are the information. So we want to see in which block of the cache this address can be stored or can be like searched. First, for direct mapping, let's look for direct mapping. For direct mapping, the first of all, the main memory is 1 meg, so we have 20 bits for entire address field. So entire address field is 20, and for direct mapping we have tag, we have block, and we have offset. Okay, so this the entire address field is 20. Now the number of blocks, the cache has 32 blocks. So 32 block is 2 to the power of 5. In direct mapping, we need 5 bits to determine the block. 5 bits. The size of each block is 16 bits, so we need 4 bits to determine the offset. So 4 plus 5 is 9, and 11 bits for the tag. Okay, so now we copy this address in this field. So we write this number in binary. So 3 is 0011, 2 is 0010, 6 is 0110, A is 1010, 0 is 0000. The first 4 byte is for offset, 4 byte. The next 5 byte, 1, 2, 3, 4, 5 byte for block, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 for the tag. So which block holds this data? Of course, block number 01010, which is block number 10 in decimal. Okay, so this one holds the block number 10 holds the data of this address. Now let's look to fully associative. Part B. The fully associative has this mapping. We have offset and we have tag. Of course, entire address field is 20 bits. The offset, as we discussed, is 4, and the remaining is 16 for tag. Because it's fully associative, it could map anywhere. In fully associative, it could map anywhere in any of those blocks. So anywhere. So block number, let's say 0 to block number 32, 31. So in all of the blocks, we can map if it is fully associative. The next one is set associative. For set associative, we have this address field divided to 3 sections: tag, set, offset. Of course, each block is 4 bits, so 4 bits here. Set. Let's go back to the problem. It says that it's four-way set associative. How many blocks do we have? We have 32 blocks. So how many sets do we have? 32 over 4 is 8. So we have 8 sets. So for 8 sets, we need 3 bits, and the total is 20. The remainder is 13. Okay, so if we write the number here, we will have 0 0 1 1 0 0 1 0 0 1 1 0 1 0 1 0 0 0 0 0. Okay, so this one is the address. So we can say that the address will be mapped in set number 2 in any block in set number 4. In set number 4 we have 2 blocks. Sorry, we have how many blocks? 4. Yeah, we have 4 blocks in set number 2, and this address can be mapped in any of those 4 blocks in set number 2. Okay, so